Today, I'm going to talk about identifying information disclosure in web applications with retroactive auditing. Data breach is an enduring problem in today's web. News are full of reports about users' private information being compromised as a result of vulnerabilities in websites. So what can we do about it? Well, people have devised several techniques to deal with this problem. Before a data breach happens, we have many prevention techniques, such as privilege separation, encryption, and so on. However, regardless of these efforts, data breach still happens because we are human and we make mistakes. So what people can do after a potential breach is try to control the damage. But the problem with damage control is that it is usually quite costly. So first, institutions are often required by law to notify the victims of data breach in a timely manner. Yeah, this is the message I got from Trace yesterday that told me that all my contact information in Trace has been compromised. So yeah, if you have a smartphone, you can also download Trace app, log into your account, and enjoy the same message. Okay, so even worse, in the case that users' financial information is also breached, then they are also required to pay the victims for services like credit monitoring and fraud protection. So hopefully this is not the case for Trace if we still trust them. But University of Maryland is not that lucky. So when University of Maryland discovered their website was compromised earlier this year, which contains the social security number for all of its staff members and students, they pledged to offer its 300,000 victims for 5 years of credit monitoring service. This is gonna be a lot of money for a public school. Fortunately, there is an opportunity because in many cases, some of the data might not have been disclosed as a result of the vulnerability. In the best case, if the vulnerability might not have been exploited yet. So in this case, actually we don't have to do anything at all. Even when the attacker breaks in, she might not have gained access to some of the data. So one important goal here is to precisely identify breached data items. If we could do this, we can target the damage control at real victims only and reduce the cost. The state of the art of doing this is to use the access log. We first log all the accesses to the sensitive data and then inspect the logs after an intrusion. However, there are several problems with this approach. First, we need to know what is the sensitive data and tag them in the program beforehand. And second, because the log contains both legal and illegal accesses, we need to somehow to tell them apart. And this is gonna be a labor-intensive and time-consuming task. For example, in the University of Maryland case, it took them about a month to inspect all those breached records. So our solution to this problem is a system called RAIL. The goal of RAIL is to precisely identify previously breached data items after a vulnerability is being fixed. So here's how it works. Suppose we have a vulnerable web application, and we assume that at some time, an attacker exploited the bug and retrieves Alice's sensitive data. And after that, the administrator patches the code or fixes the access control list, which eliminates the bug. Then RAIL will replay the application, and this time we notice that only attacker's own data is sent to the attacker. And RAIL notices the difference and generate a breach report which contains only Alice's data. As we can see, RAIL's report highlights that for every session, which data item and which fields in the data items are illegally disclosed. So the key challenge for RAIL is that the application's state during replay can diverge from its state during original execution. This might not be a problem for previous system that uses record and replay because their focus is on integrity. So they either don't quite care about state divergence at all, or they stop re-execution right before the states start to diverge. In contrast, Rail's focus is on confidentiality, and any state divergence could result in a report. So, for precision reason, Rail must match up the states and try to minimize the state divergence between the two executions. Our work makes the following contributions. First, we propose a record and replace scheme suitable for identifying data disclosures. We propose several techniques to achieve this, and we implement a prototype based on Media Web Framework. And our results shows that Rail requires few changes to applications. It is precise and fast. Rail focuses on web applications only, and our prototype is based on a Media Web Framework, but our approach is not limited to Media itself. And Rail does make a few assumptions. For example, it trusts the shopware stack below the web application, which includes the web framework, the runtime system, the DBMS, and operating system, etc. Rail also assumes that the requests from the clients do not change during replay, and also the requests are serializable. So the basic approach of Rail is to record and replay the web application and then compares the output of the two executions. First, the application developer writes the application using Rail's API, and then the administrator starts the application in recording mode. As a request comes in, Rail will log all the inputs, outputs, and the execution history into a persistent log. And then later, the administrator may patch the code and restart the application in replay mode. And Rail will replay the application based on the information in the log and generate a potentially different output. Finally, Rail will compare the two outputs and report any difference. There are a few technical challenges in doing this. First, to make the report easier to understand, we need to compare and identify data items at object level. And second, because the application might read some non-deterministic values during execution, such as date, time, and random numbers. So to improve precision, we need to make sure that the replay is still deterministic. And third, for performance reasons, we don't want to replay all the requests, but only selectively replay those related to the attack. And finally, we want to minimize the programmer's efforts of porting applications to Rail. So the core in Rail's design is an action history graph, which keeps track of the dependencies among actions and objects. Actions are triggered by external events, such as requests from the clients or the timer in the server. Whenever a request comes in, Rail will create an action, and all the application code that serves these requests will run in the context of this action. As the code runs, it might access some other objects, and Rail will connect them to the current action in the action history graph. As we can see here, there are both read dependencies and write dependencies. And Rail will store the action history graph in a persistent log, as we mentioned before, and the log is consulted during replay. Now, let's look at how replay works. Rail replays each action sequentially in time order, and it replaces an action if any of its inputs or outputs are changed. Now, for example, suppose the administrator patches the application, patches code, and during replay, Rail will detect that the code object has been changed. So it goes on, it replaces all the action that depends on the code in the same order as in the original execution. Here we can see action number 2 is skipped because it's unrelated to the code object. Now, suppose that according to the action history graph, action number 4 also accessed some other object during normal execution. And during replay, one of them is being overwritten with a different value. And Rail will detect the difference and goes on to replay all the future actions that depends on it. It's worth noting that this replay process is guaranteed to terminate because Rail never runs an action which happens earlier than the current replaying action. In order to make selective replay works, rail must intercept all accesses to global objects, which includes inputs, outputs, database items, and session states. It has to do so for two reasons. First, it must check the dependencies between actions. And second, it needs to make continuous checkpoints for all the object states. To achieve this, Rail asks the developer to wrap all the global objects in the application using Rail's Object API. Well, you might say, oh no, this is gonna be a lot of work and I'm not gonna using it. But don't worry, because most of the global objects are quite standardized across all web applications. So actually, most of the wrappers can be done only once inside the web framework. Let's look at an example. Here is a code, server-side code written in Medial framework. The code defines an RPC method called submit that allows user to submit answers to homework. So when porting this code to Rail, the only thing that the developer needs to worry about is the way she accesses the date and random numbers, but nothing else. So as we highlight the change here, as we can see, there is only a single explicit use of Rail's object. And when the changed code runs, Rail will connect this input context object to the current action. And we will talk about this object very soon. However, in all other parts of the code which the user didn't change, also implicitly access many Rail objects as they run. And Rail will connect them in the action history graph as well. As we can see, there are many different kinds of objects in the action history graph. To simplify object handling, Rail provides a uniform API for all of these objects. As long as the developer uses an API to access objects, Rail will take care of dependency checking and checkpointing. So one benefit of this uniformity is that the view object also fits into this interface. And the view object is the key for Rail to check the data items in its output. So Rail maintains a view object for every session, which checks all the data items that has been sent to the client. To check a data item sent to the client, the developer simply adds an object to the current session's view object, as the code shown here. So in practice, this can be done by changing the template rendering system in most modern web framework. During replay, Rail will rerun relevant actions and recompute the view object for every session. If it turns out that there is a difference between the old view object and the new view object, Rail will report a breach. Now, recall that Rail must minimize the state divergence in order to reduce false report. This might be a problem when the application takes some non-deterministic input. Let's look at an example. The code here tries to populate a number of administrator accounts using a loop and assign them, each of them, a different random password using masked random. Now, suppose the developer decides to remove Mallory from the list of the administrators. How does Rail handle this during replay? One strawman approach is to return a new random number during replay. Of course, this is a bad idea because during replay, both Alice and Bob will get a different password, and which causes state divergence and in turn results in a lot of false reports. A better approach is to log and return the random number in the same order as in the original execution. However, this doesn't work here as well because Mary is in the middle of the list. If it's removed, then Bob will get Mary's password during replay, and the same bad thing will happen again. So to avoid the false report, Rail must reconcile state divergence of the two executions with respect to non-deterministic input. Our solution is to ask the developer to use an input context object to access non-deterministic input. So in the previous example, instead of using math at random, the developer creates an input context object and supply a stable user ID with that object. And RAIL ensures that during replay, the input context object with the same context ID always generate the same random number. Here, we choose to use the administrator's name as context ID because they are semantically stable and they are not supposed to change across recording and replay. There are some other issues that I don't have time to talk about. If you have questions, you can look at the paper. Now let's focus on evaluation. Our evaluation is based on 3 real-world applications. Submit is a homework grading website. And Endo app is a medical survey application. Telescope is an open source social news application. For each of these applications, we designed several attack workloads which represent common human mistakes, such as errors in access control list, and like stolen password and bugs in the code. The last one is particularly interesting because it's based on a real bug in Telescope's commit history, in which it does the permission checks based on the client-supplied user ID. First, let's look at the effort of porting applications to RAIL. As we can see here, for all the 3 applications, RAIL requires only less than 25 lines of code change. And most of the changes are related to non-deterministic inputs. RAIL could achieve this good result because the framework wrappers actually offloads most of the burdens from the application developer. In our Meteor prototype, we changed about 400 lines in the framework, which are shared among all the 3 applications. Next, let's evaluate how precise is RAIL's report. To do this, we run the 3 attack workloads with some other benign workloads in the background and count the number of data items reported by RAIL versus the total number of accessed ones. As we can see, RAIL only reports a small number of illegal accesses. And we manually examined RAIL's reports and found that there is no missed report and there is only a single false report, which we believe is not a problem because actually that's a malicious account created by the attacker, which is sent out as well, but it's not literally a breach, but somehow related to the attack. Next, we're going to evaluate how RAIL's selective replay performs. We compare the number of requests replayed by RAIL versus the total number of requests. As we can see here, RAIL replays only a small fraction of the original requests that are related to the attack. In the worst case is for Telescope, which RAIL replays about 10% of the requests. This is because the changed code, the patch code, is actually on a critical path of all the logging requests. So RAIL has to replay all the logging requests in order to figure out all potential leaks. We also measure the time, replay time, and find out that it's proportional to the number of replay requests, which is much shorter than the time we spend in recording. Finally, we measure RAIL's overhead during recording. As we can see here, for an underloaded server, RAIL incurs about only 5% of throughput overhead for submit workload. And in the extreme case where we have an overloaded server, the overhead is about 22%. RAIL's storage overhead is also low. It's about 0.5 kilobytes per request. So for a full-loaded server, as we show here, so it's about 500 gigabytes per year. This means that RAIL is useful in many real-world applications. Okay, RAIL is related to previous work on record and replay, but focuses on privacy instead of on integrity. RAIL also differs from previous work on detecting data breaches in that it reports on illegal accesses instead of all accesses. And also, RAIL doesn't need to tag sensitive data beforehand. In conclusion, RAIL is a system that can precisely identify breached data item after disclosure. in web applications. It provides developers with APIs that help them to identify data items, check dependencies, and match up states. It requires few changes to application, and it is precise, efficient, and practical. Thank you, and I'm happy to take questions.
Any question?
And I'm from Yale University. So I'm interested in the selected reply to the non-deterministic input. So my question is, did you implement the second strawman solution? So if my understanding is correct to your work, maybe in some scenario the second strawman solution works. I guess maybe, but did you implement that and test how bad it is, or whatever the scenario is, your solution, asking the administrator to input the, works, better than the second strawman solution.
Okay, yeah. So the second strawman definitely works for some cases, and but in our benchmark, actually we have the submission, the application, which have a feature that's to match up like students, different students, a pair of students for peer review. And though this application actually generates a lot of like random numbers, and if it turns out that one of them is like being deleted by the patch, then yeah, these things will go wrong for our application. Okay. Yeah, but it works, yeah, for some other cases.
Thanks.
Yeah, thank you.
Hi, Stefan from Google. Can we go back on the Fred model?
Which one?
Actually, the very first slides we talk about the Fred model.
Oh, okay.
Because it sounds like you're mostly protecting against effectively bad ACLs and this kind of thing, right? It's not really more like full-on code injection, right? If I'm able to inject any random code into your process, I can bypass load logging. I can just. Does that make sense? I mean, you won't be able to track what I'm doing after that point.
Yes, yeah. Our assumption is that we trust everything under the web application, so it's not the case.
Right, including the web framework, including the other stuff running on top of the concretely V8 engine.
Yes.
That is in the same process. I mean, you have one lambda here, one lambda there, and somehow we decide that the application can be quote-unquote compromised, but not the web framework that runs in the same VM, same everything, right? So I guess if you go back to your to the attacks you have, if I have a root password,
which application?
The attacks you have at the end, I think.
Okay.
If I have the root password to the box, I'm not going to bother with any of this, right? I'm just going to lift the files beneath your framework, and there's not going to be any logging left, right? Do you see what I'm saying? I'm really struggling with that.
So
realistically, what a Fred model would be here, because I just don't see how that lines up. The only thing that I can see line up is things like, yeah, an ACL error. It's purely misconfigured and nothing else.
Yes. So yeah, in this case, the administrator just fix the access control error, and then there will be a difference in a database, and Rail will detect this and replay all the relevant requests. So what is your concern here?
The second one, stolen password.
Okay. Yeah.
If I have the root pack count, I'm not gonna bother with any of.
Yeah, because like Rail actually has a like recovery script that the administrator could supply, and in the script you could just look for those malicious, suspicious requests that from a particular IP address, and then you mark all those requests as invalid.
Yeah, I think we'll take it offline and discuss that more.
Great idea. Okay, let's thanks the speaker one more time.
Thank you.